Welcome to the video solution of your selected question from the Mathematics the Easy Way DVD. If you have not yet seen the introduction video on the DVD, please do so now, as it outlines how the Easy Way series will help students to be successful in their CXC exam. While the Easy Way video solutions will help to cement the understanding of certain special questions, the solution books are still absolutely necessary as they cover all the various types of questions that are set in CXC exams. We are now at question 11, the last question of this CSEC Math January 2013 exam, and this part A is a vectors question, and what we are presented with is a parallelogram OKLM, and we are given the vector OK, that's a position vector of K, equal to V, that's this vector here, and we're also given the vector OM, that's a position vector of M, equal to U, and that's this vector here. We're also told that the point S right here on the line KM, this is KM, is such that MS is equal to 2 times SK. This is a scalar equation, and what it means is that the length of MS is 2 times the length of SK. Now, vectors can be solved using several different methods, and for this one I'm going to show you a neat way of solving vectors questions, and it involves finding the position vector for each point in the system. And for this parallelogram with these 4 points, this O is our reference point, and so we want the position vector of M, this was given, the position vector of K also, this was given, and so we would want to find the position vector of L and the position vector of S, that's OS, in order to answer any question relating to these points. And so this method is called the position vectors based method, and the first aim is to find the position vector for each point in the system. In this case, we want to have the position vector for each of these 4 points. O is our reference point, and therefore we want OM, which we have, OK, which we have, we want to find OS, and we want to find the vector OL. And we would have to use the information provided about the parallelogram and also about the point S to find the position vectors of S and L. And so let's show how this would be done. So the first thing we want to do is deduce all the position vectors, because as I said, we are using a position vectors based approach to solving this question. And now, because this is a parallelogram, it means that OKLM has 2 pairs of equal opposite parallel sides. And the first thing to recognize is that the length and direction of ML is the same as the length and direction of OK. And therefore, the vector ML is equal to the vector OK. And the vector OK were given as V, and therefore the vector ML is equal to V. Similarly, KL is equal in length and has the same direction as OM, and therefore the vector KL is equal to the vector OM, which was given as U, and so the vector KL is equal to U. So in terms of identifying the position vectors we have and the ones that we want, we were given firstly these 2 position vectors. We were given the position vector of K, that's OK, we were given that as V, and we were also given the position vector of M. Vector OM is equal to U, and based on this parallelogram we can deduce the position vector of L, because to go from O to L we would go OK plus KL, and so we are going V plus U, that is OL is equal to V plus U, and this is it. The vector OL is equal to V plus U. OL equals V plus U. And so now we only need to find the position vector of S. But to find the position vector of S, we have to use the information here that was presented about the point S. Now we're presented here with the scalar equation that MS is equal to 2 times SK. And what we can do is firstly convert this scalar equation into a vector equation. And to convert this scalar equation to a vector equation, we have to ensure that the direction M to S, which is this direction, M to S is this direction, is equal to the direction of SK, and that is so. SK is this way, and so MS and SK are in the same direction, and because they have the same direction, that is it, ms has the same direction as sk, we can input the vector component into this scalar equation to convert this scalar equation into a vector equation. And this is it. Because ms and sk same direction and ms is 2 times sk, it means that the vector ms is equal to 2 times the vector sk. And so what we have here is a vector equation with the point s. In this vector equation, ms and k are the 3 points represented. We know the position vector of m and we know the position vector of k, and therefore s is the only unknown in this vector equation. And any equation with one unknown, in this case s, can be solved for that unknown. And in vectors, we solve for an unknown position vector by splitting this vector equation into position vector. So we will split this displacement vector ms into its position vector components, and we will also split this displacement vector sk into its position vector components. And this is it. The vector ms can be written as os minus om. That's o times the last minus o times the first. The vector ms is equal to os minus om. So we have replaced ms on this side of this vector equation with os minus om. And then here, the vector sk, we can split this vector sk into ok minus os. That is, the vector sk is equal to ok minus os. O times the last minus o times the first. And this 2 remains outside the bracket. And so what we need to do is expand this bracketed term, group the os terms on this side, and so we can find the vector os, which is the position vector of s. So firstly, I'm going to expand this bracket right here, and when I expand that bracket, it becomes 2 times ok minus 2 times os. And now I will take this 2os over onto this side to add to the os over here, and this minus om, I'll take it on this side, and so we will have 3 times the vector os on this side and 2 ok's here, and then this minus om comes on this side to become plus om. And since we know that ok is equal to v and om is equal to u, this vector equation reduces to 3os equals 2v plus u. 2 times ok becomes 2v and om becomes u. And so 3 times vector os is equal to 2v plus u. And to make os a subject now, we simply divide through by 3. And when we divide through by 3, we divide each term by 3. And so that reduces to the vector os equal 2/3 v plus 1/3 u. That's 2 divided by 3 times v, that's what we get here. And u divided by 3 is the same as 1/3 u. And so we now have the position vector of s and can proceed to answer the questions because we have the position vector for each point in the system. So now we can proceed to answering the questions. And so what we have so far is the position vector of k, which is v, the position vector of m, which is u, the position vector of l, which is v plus u, and the position vector of s, which is 2/3 v plus 1/3 u. And the first question wants us to calculate the vector mk, the displacement vector mk. And the vector mk is simply equal to ok minus om. That's o times the last minus o times the first. That is the position vector of the last is k, minus the position vector of the first, where the first is m. Vector mk is equal to ok minus om. O times the last minus o times the first. And therefore, this is simply v minus u because ok is v and om is u. And so we have found the vector mk. Next, we are required to find the vector sl. And similarly, the vector sl is a displacement vector, and it is equal to o times the last minus o times the first. That is ol minus os. And this is it. The vector sl is ol minus os. And we have ol equals v plus u, and we have os equals this expression here. And so we can go ahead and show that calculation. So the v plus u here is OL, and then we are subtracting, that's minus OS, and OS is this term here. So we will expand this bracket, and since we are working in thirds, we can convert these two terms to thirds by multiplying this V by 3 divided by 3, and also multiplying this U by 3 divided by 3, and so 3 will be in the denominator of all terms, and we'll be able to add these fractions far more easily. And this is it. This negative is applied to the two terms in this bracket, and so we end up with minus 2/3 V from here, and then minus 1/3 U gives us this minus 1/3 U here. And then, as I said, this V, we write it as 3 divided by 3V, and this U, we write it as 3 divided by 3U, and this is in an effort to make all the denominators the same. And so we can add the two terms in V, that's 3V minus 2V, both of them divided by 3, and 3U minus 1U, again, both of these divided. And when we do that, the result is this: 3 minus 2 divided by 3V, that's the result of adding this term, and 3 minus 1U gives us 2U over 3, and this term here, 2/3 U, is a result of adding this term and this term, and so this vector here is our vector SL. And finally, we're asked to find the vector OS, but we already have the vector OS. This is it, and so we can just simply go ahead and write that vector. So that is the answer. Once we have the position vector for each point in the system, then all these displacement vectors can be found quite readily. And as you have seen, we would have already found our vector OS. That's the position vector of S. Okay, so I've decided to insert this section where I'm looking at a method 2. And in this method, I'm going to basically be using the diagram to guide us through the solution. What we have looked at before was a method where we focus on using position vectors, but this time I'm going to use the diagram, right? So I've left what we have decided so far, which is that because it's a parallelogram and this side and this side are equal and parallel, then if this vector is V, then this vector also is V. And similarly, this side and this side are parallel and equal in length, and so if this vector is U, then this vector also is U. So I've left that on the diagram. And then now we are focusing now on the fact that the point S is on KM, such that MS is equal to 2SK. MS is equal to 2SK. We're going to use this information to see how this line MK is divided. Alright, so let's proceed. So as I said, I'm using the diagram, and as we said before, because the direction M to S is the same as S to K, then it follows from this relationship, which is a relationship of the length, that the vector MS is equal to 2 times the vector SK. Now a neat way of showing how S divides this line based on this equation is to actually put the information from this equation on the line segment. Alright, and it is that the MS piece is equal to 2 times SK, and this is the SK piece. So if I can show this information on the line, then we can see how we can basically divide the line into a ratio, and this is it. The MS piece is equal to 2SK, and I'm saying that the SK piece is 1SK, and so if I remove the SK from here and here, I am left with the ratio of the line, and so the line by this equation is divided in the ratio 2 to 1, and so MS is 2 parts of the line MK and SK is 1 part of the line MK, and so the ratio of the line is basically 2 to 1. So we can see that the total parts on the line is 3 parts, 2 parts here, 1 part here, and we can therefore establish and see that MS therefore is 2/3 of MK and SK is 1/3 of MK, and that will help us to proceed through the solution fairly quickly. So this is what we are deducing from this observation. MS is 2/3 MK, that is MS is 2 out of the 3 parts of MK, and SK is 1/3 of MK. That is it. SK is 1/3 of MK. And with this information, we can basically now use a diagram to see how we go from point to point going along these vector directions that we know. So we're at the stage now we can actually now look at answering questions. And first part wants us to find the vector MK. And if you look at the diagram, to go from M to K, we can go M to L and then L to K. So we can write that as an equation. MK is equal to ML and then LK. The and then really is the plus. So going from M to K is the same as going from M to L and then L to K. On the diagram, MK is equal to ML plus LK. Now if we are to insert the vector components now, the ML is V, that's from here, the ML is V, and then now the LK is minus U, because U is this direction upward, but we are going LK, we are going in the opposite direction to U, and the opposite direction is represented by this minus sign. And so going from L to K means that we are going on the vector minus U, and therefore the vector MK is simply V minus U. And we have basically established that by just observing the diagram. Let's look at part 2. Now part 2 is asking us for SL, and again we can look at the diagram to see how we go from S to L. Now to go from S to L, we could come down to K first and then go from K to L. And so we can write that equation, that SL is equal to SK plus KL. That's it. Going from S to L, we can go S to K and then K to L. But as I have said, the SK is 1/3 of MK, and it's good to reference SK in terms of the MK because we already know that MK is V minus U. So we're going to rewrite this equation and replace the SK with 1/3 MK, and basically this is it. And so SL is now equal to 1/3 of MK plus KL. The KL is obviously U from here, and the 1/3 MK now becomes 1/3 of this. This is MK, and now we want 1/3 of this MK. So 1/3 of MK will become 1/3 V minus 1/3 U. So now we can show that, and that's it. This is 1/3 MK, 1/3 V minus 1/3 U plus KL, which is U. And then all we need to do now is simplify this. Now this is a U term and this is a U term. This is the only V term in the expression, so this will come back as 1/3 V. But to calculate this, we can look at this as being U minus 1/3 U. So a whole U minus 1/3 U will basically give us 2/3 U. And so we can write the answer. The answer is that SL is 1/3 V plus 2/3 U. And this is the same answer we got when we did it using the position vectors method. And now if we look at part 3 is now asking us for the vector OS. The vector OS is the vector that will take us from O to S. So we go from O to S, we can go O to M and then M to S. And we can therefore write that equation, that OS is equal to OM plus MS. OS is equal to O to M and then M to S. And again, we have the MS written in terms of the MK. And it is good to have the MS written in terms of the MK because again, we know what MK is. MK is V minus U. So I'm going to rewrite this equation as OM plus 2/3 MK because the MS here is 2/3 MK. This OM is coming back unchanged. And now if you look at the diagram, the OM is simply equal to U, and the 2/3 MK becomes 2/3 of this because this is MK, and 2/3 of this is really 2/3 V minus 2/3 U. And so we can show that, and this is it. The OM is U, and we're adding 2/3 MK, and this is 2/3 MK. This is MK, so this is 2/3 MK. 2/3 V minus 2/3 U. That's it. 2/3 V minus 2/3 U. And then we're adding these two U terms now. This is the only v term, so this will come back unchanged, and now it's u minus 2/3 u. A whole u minus 2/3 u will give us 1/3 u, and so we can write the answer. This is the 2/3 v coming back here unchanged, and this is the result of the u minus 2/3 u. U minus 2/3 u is 1/3 u, and so this is the vector OS. And basically these are the same answers that we got when we use the position vectors method. I believe some students might prefer to do the question this way, but it's good when we can actually solve a question using multiple approaches. What I want to ask students to do now is actually try to calculate part 2 and part 3 by going in other directions. So for example, the SL, going from S to L, we could have gone S to M and then M to L. And note that SM would be minus 2/3 of MK. Minus 2/3 of MK, because MK is in this direction down. But if we are going S to M, it will be minus 2/3 of MK. Right, so I'm giving that as a hint. So we could have gone minus 2/3 MK plus V. We would end up with the same answer that we have here. And then going for the OS, to go from O to S, instead of going O to M and then M to S, we could have gone O to K and then K to S. Again, K to S will be minus 1/3 of MK, because we are going in the opposite direction to MK. It would have to be minus 1/3 of MK. So to go from O to S, we could have gone O to K and then K to S. The O to K would be V, and then the K to S would be minus 1/3 of the MK that we have here. So I would ask the student to try calculate the SL and the OS by going in those opposite directions or those other directions, and your answer is supposed to come out to be the same as what we have here. Alright, so just wanted to insert that part as another method, and we will now continue with the remainder of the questions in this exam solutions. Let's move down now to question 11b. Now question 11b gives us this matrix 0, -1, 1, 0 representing a single transformation, and we are told that the point 5, 4 is the image of P under transformation J, and what we want is the coordinates of P. Now since 5, 4 is the image of the point P under transformation J, it means that when the matrix J is applied to a point P, the result is the point 5, 4, and we can represent that information this way. The point P, which we don't know, which we are trying to find, we can call it AB, and the point P under transformation J is mapped onto P prime. P prime is the point 5, 4, and what it means is that when the matrix J is applied to the point P, the result is P prime. And so the calculation for this transformation is this: the matrix J multiplied by the column vector for the point P is equal to the column vector for this point 5, 4. And so we have set up a matrices equation, and in this matrices equation, this 5 here is obtained by multiplying this first row by this column here, because this 5 is a first row first column element, and so we'd have to multiply this row by this column to get this 5, and then this 4 here would have to multiply this row by this column to get this 4, and so we can set up those multiplication to find our value for A and our value for B. And this is the first one. The row 0, -1 here multiplied by the column AB is equal to 5, and that's what this is saying. And so to carry out this calculation, we multiply along this row down this column, and so 0 multiplied by A plus -1 multiplied by B is equal to 5, and this is it. 0 multiplied by A is 0 here, and -1 multiplied by B is minus B here, and that calculation is equal to 5. And if 0 minus B is equal to 5, it means that
B is equal to negative 5. And so we have found the value for B. And then as I said, this 4 is this row multiplied by this column. So let's show that. And this is it. The row 1, 0 here multiplied by the column AB is equal to this value 4. And so 1 multiplied by A plus 0 multiplied by B is equal to 4. And so we can show that 1 multiplied by A is A, 0 multiplied by B is 0, and the result is 4. And so if A plus 0 is equal to 4, then A is equal to 4. And so we have found the coordinates of the point P. P, therefore, is the point 4, negative 5. A is 4, A is 4, and B is negative 5. B is negative 5. And therefore, that's the answer for this question. The point P is 4, negative 5. Let's move down now to question 11C. Now in part 1 of question 11C, we are required to write down the 2 by 2 matrix H, which represents an enlargement of scale factor 3 about the origin. And so the components of this enlargement, k equals 3, k is the scale factor, and the center of the enlargement is the origin 0, 0. And therefore, that enlargement matrix is a matrix K0, 0K. That's a matrix for an enlargement about the origin where the scale factor is K. And in this case, K is equal to 3. And so that's the answer for part 1 of question 11C. Now part 2 wants us to find the coordinates of the point 5, negative 7, which we have called Q, under the combined transformation H followed by J. And this combined transformation can be represented in this way. The point Q is first transformed by H, which is 3, 0, 0, 3, onto a point Q prime, and then the point Q prime is transformed by J, which is 0, negative 1, 1, 0, onto Q double prime. And our aim is to find this Q double prime. This is the image of the point Q under the combined transformation H followed by J. And so to carry out this combined transformation, we can firstly apply the matrix H to this point 5, negative 7 to get this point here. And then once we have this point, we can apply the matrix J to this point to arrive at this final position. But because the two transformation matrices involved are 2 by 2 matrices, this transformation, which involves 2 steps, can also be completed in 1 step. And this is the indication of that. If we are going to do this combined transformation H followed by J in 1 step, we have to use the matrix J multiplied by H. That's the second matrix multiplied by the first matrix. What we say here is that we apply the second transformation to the first transformation. And so the single matrix which would map Q onto Q double prime in 1 step is the matrix JH. We would have to multiply the second matrix by the first matrix to find that single matrix which will do this combined transformation in 1 step. And so this is it. We can do this combined transformation H followed by J in 2 steps here, where we apply H first and then apply J, or we can do it in 1 step where we apply a compound matrix J multiplied by H, the second matrix multiplied by the first matrix. And for the benefit of understanding this concept, I will use the 2 methods to carry out this combined transformation. But firstly, we have to calculate the matrix JH, and this is it. JH is equal to the matrix J, that's here, multiplied by the matrix J. And when we multiply these 2 by 2 matrices, the result is going to be a 2 by 2 matrix. And here we will show how these elements are calculated. This first element A is in the first row and the first column, and therefore we have to multiply this first row by this first column to get this element A. And that calculation is done along the row and down the column. So it is 0 multiplied by 3, which is 0, and the negative 1 multiplied by 0, which is also 0. And so the element A is 0. This next element B is calculated by multiplying this first row by this second column here, because this element B is in the first row and it's in the second column here. So we multiply this first row by this second column, and so it is 0 multiplied by 0, which is 0, and negative 1 multiplied by 3, which is negative 3. And so the element B is negative 3. And now this element C is calculated by multiplying this second row by this first column here, because this element C is in the second row and the first column. And so we are multiplying this second row by this first column. And so it's 1 multiplied by 3 plus 0 multiplied by 0. So it's 3 plus 0 is 3. And so this element is equal to 3. And then this fourth element D is obtained by multiplying this row by this column. And so it is 1 multiplied by 0 plus 0 multiplied by 3. 1 multiplied by 0 is 0, and 0 multiplied by 3 is also 0. And so the element D is 0. And so the single matrix JH is this matrix 0, negative 3, 3, 0. And so this is a matrix which will be used to do this transformation, this combined transformation, in one step. And now we will go down and show the two methods of carrying out this combined transformation. And now firstly, we're going to do the combined transformation using two steps. We are finding the image of the point 5, negative 7 under the combined transformation H followed by J. And in this two steps method, we are going to apply H to the point Q to give us Q prime, and then apply J to Q prime to give us Q double prime, which is the image of the combined transformation. So first, we're going to apply H to Q to get Q prime, and so Q prime, the elements of Q prime would be equal to H, which is 300K, multiplied by the vector matrix for this point, which is 5, negative 7. And when we carry out this calculation, the result is 15, negative 21, because 3 multiplied by 5 is 15, and 0 multiplied by negative 7 is 0. So this element is 15. And then for this element here, it is 0 multiplied by 5, and 3 multiplied by negative 7, which is negative 21. And so the coordinates of the point Q prime is 15, negative 21 from here. And now we'll apply the matrix J to the point Q prime to get Q double prime. And this is it. Q prime is mapped onto Q double prime by the matrix J. And so this is the calculation. The coordinates of Q double prime are obtained by multiplying the matrix J by the vector column matrix for the point Q prime. And when we do this calculation, the result is 21, 15, because 0 multiplied by 15 is 0, minus 1 multiplied by minus 21 is 21, and so this element is 21. And then for this element, it is 1 multiplied by 15 is 15, and 0 multiplied by minus 21 is 0. So 15 plus 0 is 15, and therefore Q double prime is the point 21, 15. And so this point 21, 15 is the image of the point 5, negative 7 under the combined transformation H followed by J. Let's go now and show the same combined transformation using one step. And now in this one step method, we are going to be using the single matrix JH, which was obtained by multiplying the second matrix by the first matrix. And this is it. We are doing this combined transformation now in one step. And remember, the matrix JH we calculated was 0, negative 3, 3, 0. And so when we apply this matrix JH to this point, the result is going to be this image point of the combined transformation. And so this is it. JH multiplied by the vector for the point Q will give us the vector for Q double prime. And this is the calculation. We are multiplying the combined matrix JH by the vector column matrix for the point Q. And when we do that calculation, the result is 21, 15. and this 21 is obtained by multiplying this row by this column. 0 multiplied by 5 is 0, negative 3 multiplied by negative 7 is 21, and so this element is 21. And this 15 is obtained by multiplying this row by this column. 3 times 5 is 15, and 0 times negative 7 is 0. And so the result is the same as before. The image of the point 5, negative 7 under the combined transformation h followed by j is the point 21, 15. And that is the answer for question 11C, done two ways, by 2 steps and by 1 step. Let's move down now to question 11D. In question 11D, we are told about 3 models of phones and we are given the cost for each phone. Model A cost $40 each, Model B cost $55 each, and Model C cost $120 each. We are also given the number of each phone sold over a 2-week period. And so in week 1, 2 Model A, 5 Model B, and 3 Model C phones were sold. And in week 2, no Model A, 6 Model B, and 10 Model C phones were sold. And the first part wants us to write a 3x2 matrix to represent the 2-week sales. So a 3x2 matrix has 3 rows and 2 columns. And since we are talking about 3 phones and 2 weeks, we will place the information for the 3 phones in the rows, in the 3 rows, and the information for the 2 weeks down the 2 columns. And so the matrix for the sales will be this: week 1 sales in the first column and week 2 sales in the second column. Model A phone for the first row, Model B phone for the second row, and Model C phone for the third row. And so this will be a 3 rows by 2 columns matrix. And this is the matrix. Sales in week 1 were 2 A phones, 5 B phones, and 3 C phones. And the sales in week 2 was no A phones, 6 B phones, and 10 C phones. So this is our 3x2 matrix representing the sales over 2 weeks. Part 2 wants us to write a 1x3 matrix which represents the cost of the different phones. And so we are talking about 3 phones with 1 line of cost. And so we'll put the 3 phones down the 3 columns and the line of cost in the 1 row. And therefore the cost matrix would look like this: cost of A, cost of B, and the cost of C. 1 line of cost, 3 different phones. And so this is our cost matrix: $40 each for the A phone, $55 each for the B phone, and $120 each for the C phone. And so this is our 1x3 matrix representing the cost of the phones. Let's move down now to part 3. Now what we have so far are the 2 matrices, the cost matrix and the sales matrix. And the cost matrix is a 1x3 matrix and the sales matrix is a 3x2 matrix. And now in part 3 they want us to write the multiplication of 2 matrices which represents the sales revenue from the cell phones over the 2 weeks. So we basically want to be multiplying these 2 matrices to arrive at the sales revenue, but the multiplication of 2 matrices must be placed in an order that will make the multiplication possible. Multiplication in matrices is only possible when a particular condition is met. 2 matrices can only be multiplied when the number of columns in the first matrix is equal to the number of rows in the second matrix, and therefore the order of the multiplication of these 2 matrices must be such that those conditions are met. The number of columns in the first matrix must be equal to the number of rows in the second matrix. And let me explain. If we were to place a 3x2 matrix in front, then the number of columns in this first matrix would not be equal to the number of rows in the second matrix. Here, the number of columns in the 3x2 matrix is 2, while the number of rows in the 1x3 matrix is 1. And because these two are not matching, it means that this multiplication is not possible, and therefore we cannot multiply the 3 by 2 matrix by the 1 by 3 matrix. Instead, if we place the 1 by 3 matrix in front of the 3 by 2 matrix, what we would have is that the number of columns in this first matrix would be equal to the number of rows in this second matrix. And so, because these two numbers are equal, the number of columns here is 3 and the number of rows here is 3, this multiplication now is possible. And the result of this multiplication is going to be a 1 by 2 matrix. The result of multiplying these two matrices will be a 1 by 2 matrix, the number of rows from the first matrix by the number of columns of the second matrix. And so in order to make the multiplication of these two matrices possible, we have to place the 1 by 3 matrix, which is the cost matrix, in front the 3 by 2 matrix, which is the sales matrix. And so this is how the revenue would have to be calculated. The 1 by 3 would have to be multiplied by the 3 by 2. And when we do that multiplication, as I said, the result would be a 1 by 2 matrix, meaning 1 row, 2 columns. The element here would represent the sales in week 1, and the element here would represent the sales in week 2. And the codes R1, C1 are placed here to show the row and the column that must be multiplied to arrive at this element, and R1, C2 again represents the row and the column that would have to be multiplied to get this second element, and that is this row 1 and this second column. And so the calculation for this element would be 40 multiplied by 2 plus 55 multiplied by 5 and 120 multiplied by 3. This is it. 40 multiplied by 2, 55 multiplied by 5, 120 multiplied by 3. And the element for here would be calculated by multiplying this row by this second column. And so it would be 40 multiplied by 0, 55 multiplied by 6, and 120 multiplied by 10. And so this is how these figures would be calculated. And if we were to calculate the figure for here, that would be $715, and the figure for here would be $1,530. And so this is the sales for week 1, and this is the total sales for week 2. So that is the answer for question 11D, and that is the end of this question and the end of this production. I hope you learned a lot, and we'll do more solutions in the future.
Daddy, you're recording mathematics the easy way for me?
Yes, Kai, but you have to be quiet. Remember, you have to be quiet when I'm recording this stuff, okay?
Yes, Daddy.
To help students understand mathematics. So until next time, continue to study hard so you can pass your exam easily.
You have just seen the video solution for a special CXC question, but this is only one of the many different ways that these questions are written. All mathematical principles can only be fully understood by solving many questions, and so I always tell my students, more maths equals better maths, and if they study hard, they will pass easily. All the various types of CXC questions are covered in the Easy Way Mathematics Solution book, and you need to practice every single one of them. Other books in the series are the Easy Way Multiple Choice Specimen book, the Easy Way Unit 1 Cape Mathematics Solution book, and the Easy Way Account Solution book. Please feel free to contact me with your comments and queries at any time.